Hey everyone, I'm going to go through the problems from the test review for vectors as well as a few other examples from worksheet D, which was the applications of the vectors that we did. There are already videos of a few of the examples from worksheet D, but I figured I'd put a few more on our test review to make sure that we're good to go. All right, so starting off with our test review, we just have a little bit of vocab. So you had some on your quiz and some of you weren't thinking it would be there, but it was there. Might be there again on your test. All right, so a vector definitely is an array. It has a beginning point, but not an ending point. And you can represent it and you can determine its magnitude and direction angle. So it's an array with a particular magnitude and direction. The components tell you the horizontal and vertical values or distances that you are traveling to get to that particular ending, that direction. The magnitude tells you the length or the distance. In word problems, it could be represented as velocity. Be nice if I could spell that word, which is the same thing as speed. And sometimes it'll say like the force or the pounds of pressure that you feel when someone's pulling you or something's being pushed, something like that. All right, multiplying a vector by a scalar, how does it change the vector? It only increases or decreases its length. It will not change the direction angle because it's going the same way, just longer or shorter. What happens to a vector when it's multiplied by a negative scalar value? Then that means you are going to go in the opposite direction. So if you were originally going 30 degrees to the northeast, then you would be traveling 30 degrees to the southwest, which actually would be 210. So if you kind of think about your unit circle and where you would be. The sum of two vectors is called the resultant. So it's the resultant. There you go. And the direction angle for your vector tells you how your angle is created by the vector from 0 degrees on the x-axis. So remember, we're always starting here and traveling around until we get to wherever the vector is. Okay. And another thing just to note, bearings, which are a little bit different, actually go clockwise from the north. And remember, our bearings are the ones that actually the angles are represented super, super close to the y-axis because we're traveling in this direction instead. Okay, so just keep that in mind when we practice a few of the bearing problems. Now, going through a couple of things with our vectors. So the operations, we have vector u as 4, 3, and vector v with components of negative 6, 10. For 8a, we want to do 2u minus v. So we're going to do a scalar multiplier of vector u and then subtract vector v. So 2 times u would give us 8, 6. And then we're going to add the opposite. So plus a negative of negative 6 would be positive 6 and a negative 10 to give us our resultant. Add your horizontal components and then add your vertical components. So the sum 2u minus v gives us 14, negative 4. For example B, we're going to take half of u plus 3 times v. So scalar multiplier, half of u would give us 2 and then 3 halves, plus 3 times vector v will give us a negative 18 and 30. And then when we add those two together, again, add your horizontal components to give a resultant of negative 16, and your vertical components would be 30 and 1.5. So you can write 31.5, or you can write it in fraction form if you choose that method. There you go. So again, whether we're adding or adding the opposite with subtraction, we are still finding the resultant of the vectors. Okay, our next example, determine the magnitude. Remember, that is our length or our distance. So we are always going to use our distance formula, square root of a squared plus b squared. And the direction angle. Since we're going to have our components, we're always going to do tangent inverse of y over the x, or in our cases, b over the a, or sine over cosine, however you want to think about those. Remember, depending on where the vector lies, based upon its components, depend on what you do for the direction angle. I'll remind you when we get there. So the first thing we're going to do is find the magnitude of the vector. We'll call it vector v. So its magnitude is going to be the square root of negative 2 squared plus 7 squared. Remember, you could just write that as positive 2 squared plus 7 squared and then take the square root, because you should always have positives underneath when you square them. So the magnitude of vector v is 4 and 49, and then take the square root. So it's the square root of 53. All right, determining the direction angle. So remember, to find our theta value, we always want to use tangent because we already have the horizontal and the vertical components, the x and the y, the cosine and the sine. So I first want to visualize where this vector is. If I'm going negative 2, 7, I actually will have a vector that's drawn in quadrant 2. So let's review. In quadrant 1, theta is given, it's good. It's going to be an angle between 0 and 90, and you're done. If you're in quadrant 2, in order to find theta, you have to do 180 degrees minus your reference angle. That's actually what we're going to do in this value. I'm looking for theta, but I need to use the reference angle on the other side, that distance up from 180 to solve. I'm going to list the others so you have all of them for any other examples. In quadrant 3, to find our theta, remember in quadrant 3 we'd be a little bit past 180, so I have to do 180 plus the value of the reference angle, and that graph would look like this, and our reference angle would be this little guy right there. There's a reference angle. And last but not least, if you are in quadrant 4, you are closer to 360 degrees. So it's going to be 360 minus the value of your reference angle. And you're typically going to get negative values for those. Just remember that our reference angles, we always want to use the positive. So use its absolute value. So in quadrant 4, we're closer that way. And there's our reference angle. And I've put each of those reference angles in that little black color so you can differentiate between the two. And this is stuff that we've been doing, golly, since, well, way back in the day, Unit 4, or whatever number it was, back in the fall. All right, so back to our example. So we have the vector negative 2, 7, which I've sketched. So I went negative 2, left 2, and up 7 to create my vector, and then I can drop that perpendicular to create a right triangle. And that helps me determine and look at my reference angle. I'm going to use tangent inverse of sine over cosine, the y over the x. And tangent inverse of that value gives us actually negative 74.05 degrees. So we're going to use approximately 74 degrees as the reference angle. Now, again, that's not the angle that I want. I want theta. I want theta. Let's make that one a different color. So theta is over there. So theta, in this case, because we're in quadrant 2, is 180 minus 74 degrees, which is 106 degrees. So our magnitude of this vector is the square root of 53, a little bit more than 7. And our direction angle is 106 degrees from the positive of our x-axis, traveling clockwise as we've been doing. Oopsie, excuse me. All right, number 10, determine the component form of the vector with an initial point of -3, -5, and a terminal point of 2, 5. So for this, I know where I'm starting. I'm starting at -3, -5, and I'm ending at +2, +5. So there's the vector. So we have to take the terminal points minus the initial. Okay, so that means for the x's, I'm going to write 2 minus -3 for the horizontal components. And then I'll do 5 minus -5 for the vertical components. Simplify those, and it gives you component form of 5, 10. What that means is you have traveled 5 units to the right and 10 units up to get from your initial point to your terminal point. So that's giving you this horizontal and vertical distances. Okay, our next example, determine the component form of the vector with a magnitude of 192 and a direction angle of 312 degrees. Okay, I do not have component form. I need the x and the y. All they've given me is the magnitude of the vector to be 192, and that theta is 312 degrees. That does give you enough information to work through this problem. Think about where that angle is, 312 degrees. That is totes for sure in quadrant 4. So I'm just going to sketch it, okay? I just need to be in quadrant 4, 312 degrees. That sounds good, right about there. And here is my 312 degrees. All right, gang, what do you think we need to do? How in the world are we going to figure out this horizontal distance and this vertical distance that actually drops down? So we'll need a negative y there. If they just give me that exterior angle of 312 degrees is how I get there. Oh, they do tell me the magnitude. Don't forget to put that in there. Your magnitude is 192. So that is the length of the vector that was created. Okay, so that kind of helps. Hopefully, while I've been chit-chatting, you've thought, oh, maybe I should know this distance. I should figure out what the reference angle is. All right, so let's do that. Can we work backwards? If I have a total of, if I'm in quadrant 4, I'm really close to 360 degrees. I've traveled 312, so that gives me a reference angle of 48 degrees. Yay us. Okay, so let's pull that out so we can see it a little bit better. There's my x, there's my y, right angle. This is 48 degrees. I have a hypotenuse length, which is our magnitude of 192. So in order to solve for x, I could use cosine. I have the adjacent and the hypotenuse. So cosine of 48 degrees equals x over 192. Therefore, x is 192 multiplied by cosine of 48 degrees, which gives us 128.5. There we go. All right, now let's check for our sine value. I need my y. So in order to find sine, we're going to use the opposite hypotenuse. So sine of the angle, 48 degrees, is y over 192. Therefore, y equals 192 times sine of 48 degrees, which is 142.7. Okay, so we have found both of our components. I know that the x is 128.5 and the y is 142.7. But wait, I know someone's going to double check me on this and tell me, yo, Fairbanks, you got a goof. What do I need to fix? Okay, think back to the beginning. We are in quadrant 4, where the x's are positive and the y's are negative. So guys, make sure you slap a negative on that horizontal component to show you went to the right and down to create that vector. Good deal. Good catch. All right. Next one, determine magnitude and direction angle of the vector -3, -4. Let's sketch for visual learners. I need -3 to the left, -4 down, go back, and there we go. We are 100% in quadrant 3. So quick little recap. If you're in quadrant 3, you are past 180 degrees. So I need to do 180 plus my reference angle in order to determine theta, which is the direction angle of the entire vector. Okay, we also need to get our magnitude or our distance. If you at all remember the Pythagorean triples we talked about a while ago, magnitude is a piece of cake and you've already got it done. You don't have to do any work. For those of us that forgot, here we go. The magnitude of the vector is the square root of my distance of my x's squared plus the distance of the y's squared. So the magnitude of vector m is 9 and 16, which is 25, which has a square root of 5. There you go. Finding our angle. Again, because we are in quadrant 3, when we do tangent inverse of our ratio, so remember, we're only finding this little angle here. That's the reference angle. So tangent inverse would be -4 over -3, which is +4/3. Okay, so reference angle is tangent inverse of that value, which is about 53 degrees, 53.13. So we're going to round it to 53 degrees, keep things easy. Okay, again, that's only this little piece. This little section is 53 degrees. I need to go a heck of a lot farther than that because I'm in quadrant 3. So I'm going to do 180 plus my reference angle, 53 degrees, to get theta, which has a value of 233 degrees, 0.13 if you're adding in that extra value. All right, we are making it through. We're flying through this stuff. Good job, guys. All right, number 13, use the figure given to sketch each of these vector resultants. So our first example is to sketch B plus C. Okay, so vector B travels down and to the left. Vector C, if I am adding vectors together, I have to start at the terminal or end of B and add C in the direction that it's drawn. Okay, perfect. And the resultant is from the beginning of where I started to the very, very end. And please label it. I'm fine with the word resultant. Sometimes people like B plus C, the actual vector showing their sum. Okay, but again, you draw your first vector as is, or as it's asked. From the end of that vector, the terminal point, add your next vector, and then go back to the beginning, from the very beginning to the very end. That is your resultant. Okay, let's try again with the next one. Vector A minus C. So vector A goes up and to the left. Okay, there's A. This time we're doing minus C. So if C, vector C, actually goes down and to the left, I'm going to do the opposite. From the end of A, from its terminal point, I'm going to go up and to the right. That is the opposite of C. Okay, and we're estimating the length there, so just kind of sketch it as best you can. Wherever you began with A on its initial point to the terminal point of the new one is your resultant. Again, please label as the word resultant or vector A minus vector C. Last but not least of this set, we want to do half of C. So now we're going to make it teeny tiny and then add B onto the end of it. So vector C actually starts right around the origin, goes down into the left. There's half of it, even smaller. It's about the same, just pretend it's half. Remember, from the terminal The end of C, I need to add vector B. Vector B actually drops down into the right. So there's B. Just follow that same path. And our resultant goes from the beginning of C, 1/2 C, to the end of where I added B. There you go. All done. The last few, we have our, oh no, I'm sorry. We have one more before we get to the big, huge slew of problems. Determine the magnitude and direction angle of the resultant. This one is not labeled, so you can call these vectors whatever you want. How about P and F? Why not? Now remember, addition of vectors does not matter the order. Whether I add F to P or P to F, I will get the exact same thing, and I will prove it to you graphically. So vector F starts at the origin and it goes 1, 2, 3. So it has components of 3, and then up 1, 2, 3, 4. 3, 4. Okay. So if I start at P, its terminal point, and I travel to the right 3 and up 4, this would be adding vector F. So my resultant will go from the beginning of P to the end of F. And that lands me at the point 1, 2, 3, 4, 5, 1, 2, 5, 2. Those are the horizontal and vertical components of the resultant. If you do it the other way, so let's take vector P and add it onto F. So vector P goes to the right 2 and down 2. So P would have components of 2, negative 2. So from F, I'm going to travel to the right 2, down 2. There is vector P. And again, from the beginning of F to the end of P, I get the exact same resultant. So it does not matter the order you do it. Now that we have the component form of the resultant, its magnitude is super, super easy. Square root of the distance of our x's, and the distance of the y's. Distance of x's squared and distance of the y's squared. So 25 and 4 gives me 29. So the resultant vector has a distance of the square root of 29. In this case, we can clearly see that it is in quadrant 1. So when we are determining the direction angle, theta, we'll do tangent inverse of the vertical divided by the horizontal. That's your y over your x, your sine over your cosine. And when you simplify tangent inverse of 2/5, you get that theta is 21.8 degrees. And that is perfectly fine because from the x-axis up to, we're in quadrant 1, we are golden. We don't have to worry about a reference angle. And that does look kind of like a minuscule little angle there. So about 22 degrees. All right, last section from our test review. Use the figure to determine if the statement is true or false. Okay, so I'm going to write on the graph that we have over to the side and see if and I'll erase it through every single one that we do. All right, so here's A and here's D. So does A equal negative D? So I would flip D and go the other direction. Yes, perfect, true. Love it. All right, what about our next one? Does C equal S? Actually, this one's pretty easy. C starts down here, goes up and to the right. S starts down here, goes up and to the right. Yes, true. Those two are also equal. Okay, our next one, A plus U, does that equal C? All right, let's check. Here's vector A plus vector U. Does that equal vector C? A, U. Yes, it does. That is definitely true. If you actually look at the components and give them their values, you would definitely see that number 17 is true as well. All right, number 18, v plus w, does that equal negative s? Okay, so here's vector v, and then I want to add w. Its resultant, remember, goes from the beginning of v to the end of w. Is that the same thing as negative s? Okay, so here's s. So negative s would go just the other direction. This is not equal to one another. So unfortunately, number 18 is false. Good try, guys. Doesn't work. All right, a plus w, is that negative 2d? Let's check. So here's a, vector a. Vector w does the same thing for the same distance. So there's a plus w. This is the resultant, okay? Is that the same thing as negative 2d? All right, here's d. If I double d, there we go. So there's 2d. If I do negative 2d, it would go up and, yep, true it is. Fabulous. I'm liking these true things. All right, is a plus d equal to 0? So here's vector a. And then if I add d onto that, okay, so let me sketch d onto it. D would start at the end and travel the opposite direction, the same distance. So those would completely undo each other, right? Okay, but do you get the same thing? So that one looks like it's true, but it's not. Let's look to see our actual vectors. So if I did A's component form would be 0, 2. And D's component form would be 0, negative 2. When I find their sum, I get the vector 0, 0. So we actually do just get a point. It's not just 0, it's the vector 0, 0. That's a little bit tricky. Number 21, u minus v, does it equal negative 2 multiplied by b plus t? Ooh, that's a heck of a lot to try to keep up with. All right, u minus v. So here is vector u, and vector v goes that direction, but we want minus v. So there's minus v. So there's u minus v. Okay? Let's erase that so we don't mess it up. Does that equal, let's do b plus t. So b plus t. Here's b, and then plus t. Okay, there's those guys. That's good. But I've got to do negative 2 of that. So negative 2 times that would mean it goes the opposite direction twice as long. Okay, so these guys are not true. This one is also false because of the scalar. If it was just a negative b plus t, then it would be true. But that scalar of 2 makes it twice as long, and it doesn't work. All right, last one. T minus w, does that equal b minus a? So t is this vector minus w. So w typically would go up, but instead it's minus w. And so its resultant gives me from the beginning of, oopsies, I added that to the wrong end. Holy cow, my goodness. All right, let's fix this. Let's start over. My bad. All right, here's vector t. From the terminal point, I want to subtract w. There we go. And its resultant goes from the initial of t to the terminal of w. Okay, so let's check b minus a. B is this one, and then minus a. So from the end of b, I'm going to do the opposite of a, and its resultant looks identical. So number 22 is also true. There we go. That's it for the test review, except we have not practiced any of the application problems. Again, there are videos for a couple of the even problems already done. 2, 4, 6, and 8. I'm going to do 3 more examples, numbers 10, 13, and 16 in this video. So if you need to stop and take a break, by all means do so. I'm going to continue on. Here we go, gang. All right, number 10 from worksheet D. An airplane has a speed of 724 kilometers per hour at a bearing of north 30 east. Remember, bearings are different. Got to graph that correctly. And the wind velocity is from the west at 32 kilometers per hour. Find the resultant speed and the direction of the plane. All right, so I need to get a couple of things down pat first. Let's first look at the plane. Remember, bearings. These guys are clockwise from your y-axis from the north. And it says north 30 east. So here's north 30 degrees east. So my bearing is 30 degrees hovering right here at the y-axis. And there's my vector that's drawn. I know that its speed is 700 and, well, let's stick that actually on the outside so we can see that a little bit better. 724 kilometers per hour. Okay. In order to solve this problem, we are actually going to drop our perpendicular down on the outside. So I can find still my horizontal and vertical components that way. But you got to remember, when we're doing it this way, here's our triangle now. Here's my 724. 30 degrees is on the outside. So that means I have 60 degrees in the bottom interior corner close to the x-axis. There's my 90. And now I can determine sine and cosine a little bit better. So y and x. So cosine of 60 degrees equals x over 724. So 724 times cosine of 60 will give me that horizontal component, which is approximately 362. Okay, there's that part. And then we'll do the same thing for y. So y is my sine. So sine of 60 equals y over 724. So y is 724 multiplied by sine of 60, which gives us approximately 627. Therefore, the components for the plane are horizontal 362 and vertical 627. That's only the info for the plane. Now we need to actually do that of the wind. It says the wind velocity is from the west. All right, well, that should actually be easy. So I'm starting here and I'm coming from the west, 32 kilometers per hour. So the components of the wind are just 32 horizontal, 0 vertical. Piece of cake. All righty. So if we're looking for the resultant, if we actually take the plane plus the wind, we get this resultant. So my plane plus my wind, 362, 627 plus 32, 0 gives us a resultant of 394, 627. That is in component form for the horizontal and vertical components of the plane plus the wind. And now we're going to determine its magnitude, which will give us its resultant speed, and then the direction, so the angle that the plane is now traveling with the wind having an effect on it. All right, so plane plus wind, square root of 394 squared plus 627 squared. And that will simplify to give us approximately 740.5 kilometers per hour. Make sure you use your units of measure correctly. When we are looking for its angle, this is so nice. I'm so happy we're in quadrant 1. Yay, quadrant 1. So theta, its direction angle, is going to be tangent inverse of The horizontal, the y over the vertical, 394. And theta, its direction angle is 57.86 degrees. So if we're talking about the actual bearing that we have, this would be north 50, let's round it to 58 east. Ooh, that does not look like an E, 58 east. There you go. So this is your direction angle, and this is the new bearing that you have. Good deal. All right, we got a couple more we're going to roll through. Number 13, a ball is thrown with an initial velocity of 70 feet per second at an angle of 40 degrees with the horizontal. Yay, that's easy. Find the horizontal and vertical components of the velocity. Cool, not bad. All right, so let's draw ourselves a picture. We have an angle of 40 degrees with the horizontal. So there's my horizontal. Here's my 40 degrees. Fabulous. And it tells me the initial velocity is 70 feet per second. We're finding the horizontal and vertical components. We're in quadrant 1. I know that both the x and the y have to be positive. Why in the world did I do that? My goodness, silliness. That's what it should look like. All right, so we just practiced this actually in the previous example, determining for our horizontal and verticals. So cosine of 40 equals x over 70. X equals 70 multiplied by cosine of 40 degrees. And when you type that in, x is approximately 53.6, and that would be feet per second. If you're looking for the vertical, then you would do sine of 40 degrees equals your y over 70. Cross multiply 70 times sine of 40 gives a y value, or the sine value. And that works out to be, let's see, y equals 44.995 feet per second. So go ahead and just round that up to 45 feet per second. There you go. Those are the components. If you put it in component form, and if you wanted, you could round the 53.6. You'd have approximately 54 for the horizontal and 45 for the vertical. Again, those have been rounded, so just read the directions for exactly how we want it rounded. Last one we're looking at together, and then we're done with all this. A migrating salmon heads in the direction of north 45 east, swimming at 5 miles per hour. The ocean current flows due east at 3 miles per hour. Find the true velocity of the fish. Alrighty, here we go. I hope that you guys noticed and didn't cringe that we have a bearing north 45 east. The good thing about that bearing is 45 degrees is the same as 45 degrees, whether it is a bearing or whether it is a direction angle, because you land in the same place. Okay, so that is the info for my little fishy. So here's my little fish. Boom, there he goes, swimming, trying to get where he needs to go. All right, we need horizontal and vertical components, our x and our y, and the interior angle is also 45 degrees as well. Okay, so what's that going to tell you? If both of the angles are the same, then that means both of your side lengths are going to be the same. So when you solve for x and y, you should get the same thing. Cosine of 45 equals x over, I forgot the velocity, 5 miles per hour, so over 5. So it's 5 times cosine of 45 to give us our horizontal, which is about 3.5. When you do the same thing for sine, sine of 45 equals y over 5. 5 times sine of 45 equals y, therefore that component is exactly the same distance. So the fish is swimming at 3.5 and 3.5 in the horizontal and vertical directions. All right, our water, here's our water. It is traveling which direction? East. Due east at 3 miles an hour. Boom, 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 boom. 3 miles an hour. Okay, cool, going that way. Its components are 3, 0. Guess what we do, guys? Find the resultant of the fish plus the water. We've done this before. So here's our resultant. Here is our lovely little fishy swimming. Here is the water pushing it another direction. So fish and water. And lo and behold, this guy is the resultant. So if we add the 3.5 to the 3, 0, we get 6.5, 3.5 for the components of the resultant. Now we can determine the true velocity of the fish. In other words, how fast is that little fish swimming? Alrighty, so we're looking for the magnitude. Magnitude equals length or distance, which can also represent your speed. So we're going to take the square root of 6.5 squared plus 3.5 squared, and it is going to tell us that our little fish is swimming at approximately 7.38 miles per hour. That's a fast little fish. And usually salmon are swimming the opposite direction against the current. So, there you go. That is everything for you. That should get you rolling, a good review, good set of practice so that you'll be prepared for your vectors test. Hope you guys have a great one, and we'll chat with you later.